Hi everyone, my name is Karim Ali. I'm an assistant professor at the University of Alberta. It's a great honor to receive this prize, for which I would like to thank ATO, the selection committee, and those who nominated me, and all my mentors who helped me reach this point in my career so far. Today I would like to talk to you about my journey for the past decade or so, building scalable and precise static analysis tools that actually do work in practice. But before I do that, I would like to also thank all my collaborators, including my students at the Maple Lab at the University of Alberta, students that I've been working with from Germany, and my collaborators across the board. Andre Lotak, my PhD advisor, Frank Dev, my longtime collaborator, and Eric Bodden, my postdoc host, and a few of my colleagues also from my industry collaborators that have been the main reason why I'm here today and have been playing a major role in all of the work that I'll be talking about today as well. So why are we here in the first place? Well, we all know that software bugs are everywhere. You cannot build a system that is bug-free. And these bugs cost billions of dollars every year. And these can range from simple programming errors like the infamous go to fail problem that was there in the Apple iOS code base and allowed invalid SSL or TLS connections to be accepted just because of a simple copy paste error. Or it could be a little bit more serious, like the bugs related to poor testing in the ABS software for Toyota cars that led to unfortunately fatal accidents and costing Toyota about $3 billion due to not testing for race conditions in the ABS braking system. Or it could be even more serious, like the unencrypted, unauthenticated connections that were allowed on medical devices that lead to life-threatening bugs, because then those security vulnerabilities allow an attacker, an unauthorized attacker, to control medical implants in patients without their consent. I would argue that all these errors and even more could be detected and even possibly fixed using static analysis and various static analysis techniques. But what is static analysis and how can it help here? So static analysis is a technique where you can have a program and you want to reason about the runtime behavior of the program without necessarily executing it. So you have a program, you have a property, and you want to throw these two at an oracle. We're going to call it static analysis, and that analysis can tell you, does this property hold before a given statement S or not? Once we define the analysis as such, we can actually use the analysis to implement various compiler optimizations, various developer support tools like code navigation and code refactoring, make sure that certain critical systems adhere to industry standards and government standards, and also implement various security vulnerability analysis tools. However, in practice, static analysis, especially when I started working on it about 10 years ago or so, in practice, developers tend not to use static analysis tools. But why is that? There are three main reasons that I could identify at the time. The first one is scalability. Analyses don't necessarily scale up to large code bases that developers typically use nowadays or even at the time. Precision. Many analysis tools would print out too many false positives that just disrupt how the developer would typically use the tool and just annoy them to the extent that they no longer want to use the tool anymore. And of course, usability, which is all about how the tool would integrate seamlessly into the developer workflow without having to disrupt them and force them to do a lot of context switching, which is known as a deterrent to developer productivity in practice. Today, I would like to talk to you about some of the work and the stories behind some of the work that I have done over the past years that enable specifically scalable and precise static analysis that can be deployed in practice. So the first story starts all the way back in 2010 when I first started doing my PhD at the University of Waterloo with Andre Lotak. And at the time, I didn't really know much about static analysis. And the first question I remember I asked Andre is like, where do I begin? Like, I know I want to work with you. I know I want to work on programming language, but what do you suggest I should do at first? So he said, well, you can start reading this paper. And that paper was automatic construction of accurate application call graphs with library call abstraction for Java by Wei Li Zhang and Barbara Ryder. There were too many buzzwords for me at the time that I couldn't decipher it. What's a call graph? What's an application? Why does it have to be an accurate call graph? What does that mean? What's a call abstraction? And why is it different for a library than an application? And of course, it's important to do this automatically because then you can deploy this tool in practice. And of course, that was specific to Java as one of the major object-oriented languages at the time. So what's a call graph? To know the answer to this question, I started reading a whole bunch of research papers at the time, but the two that I still remember to this point were one paper by Frank Tipp and Jens Spelsberg about scalable propagation-based call graph analyses, and the other one was by Martin Bravenboer and Yanis Margdakis about data log-based pointer analyses. And I was very excited to learn more about call graphs at the time. And I was specifically excited to know that I can actually implement my analysis using data log without having to worry about like work list algorithms or how it will terminate and so on and so forth. So I was really interested and excited to write my first analysis using data log. So I said, well, let's actually build a call graph for Java C, the Java compiler. So I implemented my analysis using data log, and I used the Iris Reasoner, which was an open source data log engine at the time. And this at the time I was using Java 1.4, so a relatively small, or an old actually version for Java, and it was only like 500 kilobytes of class files or half megabyte of class files, so not that big. And I had a very powerful machine at the time, 8 gigabytes of RAM, and the analysis took hours to finish. And I remember this was a propagation-based analysis, but not a precise one. So just a very simple analysis where I wanted to know which methods call which other methods in the program. And the sad thing about that, or the difficult part about it, is that I always got an out of memory error exception, a Java heap space exception. No matter how much heap space I would dedicate to the analysis, no matter how much memory I add to the Java process, I always got an out of memory exception. I couldn't run the analysis on Java C. So I thought maybe I took it too far. Maybe I should settle for a smaller program. So I went to the other extreme. I went to a hello world example in Java so that I can actually see and analyze and see for myself whether my analysis would even scale to that small example or not. But I also couldn't run it on the Iris data log engine at the time. And then I decided, well, I might try just another analysis tool. And at the time I was using Soot actually, so I tried Soot at the time. And Soot is a static analysis framework that was started at McGill University at the Sable group. And even with Soot, I managed to run the analysis still, but even using Soot, it took more than 30 seconds to run the analysis, run the call graph analysis. And the call graph had about 5,000 reachable methods in there and about 23,000 call edges in the analysis. And that's just like too many methods and too many edges in the call graph for just a simple hello world example. And you would imagine like how bad was that call graph? And that's how bad it was. This is actually an actual visualization of the call graph showing you all the nodes representing methods and all the edges represent call graph edges at the time. And for me, that was just like, why is this happening? I only want to know what methods my one line of code in my application is going to call into. But the problem is that the code that you are analyzing is not just this one line of code. Later, I realized that to be able to analyze that piece of code, no matter how small it is, you need to bring in all the libraries that it depends on. And since I'm depending on like Java lang system and printing and so on and so forth, it has to bring in all that baggage with it, all the library dependencies with it. And I didn't really like that. But at first I was like, am I the only one who's questioning this, or am I the only one who's facing the same problem? And looking at other research papers and the forums on Soot and forums about static analysis tools, I found out that many other people had the same problem. Many of them would like to have an ability to ignore library code or model library code somehow, and this is one of the biggest problems that they face when it comes to scaling an analysis that is still precise enough to be used. In short, what people were really looking forward to or wanted to have is to perform what I call partial program analysis. You want to analyze part of the program and model the rest of the program in a way. But what is challenging about that is that we want to do this in a sound and precise fashion. Sound meaning that your analysis will capture any potential runtime behavior of the program, and precise means that it shouldn't compute anything else. It should reduce the number of false positives that it may generate for the analysis. And on my way to achieve that, the first thing that I did together with Andre was defining the separate compilation assumption which states that if in a language like Java and perhaps other languages as well, all of the library classes typically are compiled in the absence of the application class. And following from that assumption, we were able to determine other conditions and other restrictions on how the analysis will treat the application code that it has access to versus the library code that it wants to model in a precise way. And we published this work at eCoop 2012, and in fact that was my very first conference presentation almost 10 years ago, at the time when eCoop was held at Beijing in China. And at that conference, even though I was very excited about the work, but many people, especially after my talk and throughout the conference itself and during the poster session, they kept asking me like, this is really cool. I mean, this is a great idea. We can now have sound and precise call graph analysis, partial program call graph analysis. So how can I use it in my framework? And then people would just throw names about different frameworks that analyze Java programs. And I was like, well, I actually implemented this analysis as data log analysis. So in order for you to use it, you need to use my system as it is. And then at that point, people were just like, yeah, well, I can't use it because I cannot integrate it into my tool and so on and so forth. So I remember when I came back from the conference and I had a meeting with Andre, I was like, many people want to use it, but they can't because they just cannot integrate that system into their analysis tool. And then we came up with another idea that what if we can actually implement an automated tool that, given the code that it will analyze, it will automatically generate a stub for the library that enable this partial program analysis automatically in any Java analysis framework, not just specific to our analysis. And this is how Averroes came about, as a way to perform whole program analysis without analyzing the whole program, by modeling the library methods or the library dependencies of an application. And Averroes was very successful. We were able to, in various experiments that we ran and in various evaluations that we ran, we were able to get up to on average about 600 times smaller library sizes for the model that we create versus the original library code itself. And that enabled the analysis to be on average about 7 times faster in terms of runtime and uses about 6 times less memory in terms of RAM. And all at the same time while being precise and sound. And we've actually proven this both on paper pencil proof, and we also, Andre and I worked on a proof using Coq, but we haven't gotten around to publishing it yet, but maybe we'll do that at one point soon. And I was very happy at the time because Averroes, now that it can be used in various different frameworks, it has been featured on Suts and Wala's website as an extension tool that can be used to enable partial program analysis. And also Dupe, which I started using at the beginning of my PhD, had Averroes as an option there so that to enable partial program analysis in all these 3 main frameworks of static analysis. And this is some of the work that I've been doing over the past, at the beginning of my research career, when I was doing my PhD, with respect to how we can scale up program analysis in terms of how we can build precise models for libraries and how the separate compilation assumption helps with that to enable sound and precise partial program analysis. So fast forward about 6 years or so from the beginning of my PhD, and at that time in 2016 I was at eCoop, and at the time I was just finishing my postdoc with Eric Bollen in Germany and starting my new position at the University of Alberta as an assistant professor, where I'm currently leading the Maple Lab that primarily works on static analysis research. And at that time I had various different conversations with many people, where the main theme of those conversations was like, I want to work on something a little bit different, something new, something exciting. You know, we're starting a new position. I want to do something different than what I have been doing for the past 5 years or so. And I remember I had this conversation with Julian Dolby at one of the coffee breaks. And he threw the idea that, well, Swift looks like a very cool language, and it was just open sourced a few months before our conversation at the time, about a year before then. And I asked him the question, well, I wonder if we can actually use Wala to analyze Swift. Would that be something interesting or not? But the question now is, why Swift? Why is that an interesting language to analyze in the first place? Well, it was an up-and-coming language. Like I said, it's open source, can call directly into C code. It's based on LLVM. It's a functional programming language as well. So you have first-class functions, higher-order functions. You have immutability, currying, and automatic memory management as well. And at the time, which is 2016 or 2017, the Apple platform market share was about 21% for iOS or mobile platform in general. And for desktop, it was about 13%. These numbers are probably higher by now. But Swift was a fast and growing language and was the recommended language by Apple to to develop applications for macOS and iOS. And on the other hand, Swift analysis support was not that great. So for LLVM and Clang, you have an address analyzer and a thread sanitizer, but these are dynamic analyses that require running the program for the developer to reason about the behavior of the program itself, which doesn't benefit from the fact that in static analysis, you don't need to run the program necessarily, so you don't need to come up with test cases and coverage and ensure that you have enough coverage for your whole program to make sure that you can capture all the possible runtime behavior of your program. And the other thing is, there were a few tools out there that support analyzing Swift programs, but tools like SwiftLint and Tailor, these tools basically enforce style and convention. They have multiple plugins, they support at least Swift 4, but they don't have analysis support. That was SwiftLint. For Tailor, it was primarily a linter, so again, it can enforce a style and coding conventions. It has support for command line interface and Xcode, but at the time it only supported up to Swift 3. Swift now is at version 5. And again, it didn't have any analysis support. On the other hand, when I looked at the Android world at the time, where all the three major frameworks in research support Android analysis, so Soot, Walla, and Dupe, you have other various tools called Scandroid, Droid-Infer that can reason about various security vulnerabilities for Android applications. You have FlowDroid, you can detect data leaks and run taint analyses on Android applications. Facebook Infer also supports running on Android. And a quick search on Google Scholar shows that there is about 130,000 publications at least about Android. And that was in 2016. It's way more now at the time. So there was this discrepancy between all that effort and research going to focus on Android, but almost none on the iOS and macOS side and the Swift side of things. So that is why Swift was an interesting language to explore. So why Walla? Why would Walla be a good candidate for using it as an analysis platform for Swift? Well, it has been well established for 10, 15 years or so by the Watson lab in the US. It provides various different analysis techniques. It has been used for data flow analyses, supports language server protocol, supports major frameworks like IFDS and IDE and others. And it's also a polyglot analysis framework. So it can analyze Python, Android, Java, JavaScript, and probably more languages that I even don't know about. And it can run everywhere. So at the time, Julian was very excited that Walla can actually run on your cell phone, on a computer, on your laptop, on the web, on the browser, everywhere, which was a very neat feature. So it made sense to see how we can use this, or reuse rather, the existing analysis infrastructure in Walla and repurpose that for analyzing Swift, as well as all the other languages that Walla is capable of analyzing. So at the time, Julian and I got together and we submitted an application for a Walla hackathon at PLDI, which was accepted. And at the time, Julian and I and one of my undergrad students, Noah Wenninger, and Devin Coughlin from Apple, we were there at the hackathon. And part of the hackathon was just the four of us hacking on the Walla analysis framework and the Swift compiler, and basically creating all the glue code that is necessary to make these two code bases communicate to each other. So Walla implemented in Java, the Swift compiler in C++, and all the gory C Java native interface details that I will spare you today. That was what we focused on during that hackathon. And we were successful at doing that. But in the following years, specifically in the end of 2017, beginning of 2018, I started also working with a large group of undergrad students across the country here in Canada under the umbrella of the Undergraduate Capstone Open Source Projects, which is an initiative in Canada that existed at the time that enables students from across the country from different universities to work on open source projects for the duration of a whole semester. So I worked with different students and a large group of students there to model various different Swift instructions and how we can translate that into the Walla intermediate representation to enable analyzing Swift applications. So in about a year after that, or a year and a half after that, after a large amount of effort from all those students, we were actually able to get the first working prototype as a tool paper at FSE in 2020. So there we introduced Swan as the static analysis framework for Swift that is based on top of Walla as an analysis framework. And we were able to showcase that we are now capable of running analyses like taint analysis, for example, or taint tracking for Swift code bases using the existing infrastructure analysis in Voila with all the glue code that we created to introduce the communication between the Swift compiler and the Voila analyzer. In a parallel timeline during that period between 2015 to 2020, I have also been working on precise and on-demand data flow analyses. And that started when I joined Eric Boden's group as a postdoc in 2015 at TU Darmstadt, and I worked with various different students there on building precise and on-demand data flow analysis. And it started with our work on Boomerang, a demand-driven flow and context-sensitive pointer analysis for Java that is based on top of IFDS. And that was actually another paper that we published at eCoop 2016. And that was the main reason why I actually met Julian at the time at the conference, because I was there with Johannes and Eric presenting this paper at the conference. And then that work evolved into building alias-aware data flow analyses on top of IDE so that you can automatically handle aliases without having to embed them into the flow functions of the analysis, which was a great improvement on the state of the art at the time. And that's some work that we published at UPSA 2017. And that work eventually evolved into building synchronized pushdown systems that enable highly precise, highly sensitive data flow analyses that can scale up to very large code bases. And that was a paper that we published at POPL 2019. And that paper specifically about synchronized pushdown systems was an interesting piece of work, because at the time it enabled having a decidable analysis that terminates within reasonable amount of time that is both context sensitive and field sensitive and also flow sensitive, without having to limit the analysis to any predefined k limits, which is the typical way to go which is the typical way that most analyses would do to go around the fact that you cannot have an analysis that is context sensitive and field sensitive at the same time, because that reduces to the halting problem. And this scalable and precise analysis framework that we built that I built together with Johannes Speit and Eric Boden, we use that in practice in various different contexts. So for example here, we used it in a system called CogniCrypt, which is now an Eclipse Foundation project, where we actually implemented this as an analysis that can, in the IDE of the developer, tell the developer if they have any security vulnerability due to misusing a crypto API. So here the analysis would say, well, you're using an algorithm called AES, and that is not a secure way to use it. And the reason it's not secure is that the default configuration will use a CVC mode, which is not a secure way of using AES. And you can see here in real time that the developer is now changing the code following the suggestion by the analysis. And as soon as they save, you will see the marker on the left gutter here going away. It took about 250 milliseconds actually for that marker to go away. So SPDS, or synchronized pushdown systems, enabled us to have a very scalable, very fast, very responsive analysis that we can embed it into the IDE of the developer while still generating precise results. And that was not the end of it. We are actually able to run two large-scale studies, one on all Maven Central repositories. That's about 2.7 million artifacts at the time. And having that high level of scalability and precision allowed us to run the analysis. On average, it took about 10 minutes per artifact on Maven. And from the dataset that uses crypto APIs on Maven, we unfortunately found that 63% were insecure, which means that each one of those repositories or artifacts would have at least one security vulnerability due to crypto API misuse. And we ran another large-scale study on 10,000 most recent Android apps on Android Zoo at the time. And we found also, unfortunately, that 95% of them are insecure due to using or misusing Java crypto APIs. We were also able to reveal some new vulnerabilities, and this one was for the semantic Norton identity safe, which we were able to run and we were able to detect thanks to the high level of precision that SPDS enabled at the time. So while I was trying to build this Swift static analysis frameworks, I was also working with my colleagues on scalable and precise on-demand data flow analysis. So in the year 2020, after we published this POPL paper, I started to wonder if we can actually use SPDS as the analysis engine for Swan, and whether it would actually work for Swift or not. We know that it worked for Java, and we know that it worked for Android, but does it also work on for Swift? Completely different language, completely different infrastructure, and I started wondering about that. And during one of the group meetings, I was talking to one of my undergrad students, Daniel, and he said, well, that sounds like a really cool idea. I'd actually like to try it out. And I was like, okay, that sounds great. Well, but you probably need to read a few papers first so that you can know what SPDS is about and all the background that goes all the way back to at least until 2003 with one of Tom Repp's papers about weighted pushdown systems and how we can use it for static analysis. And Daniel and I spent a lot of time from 2020 until July 2021 this year. Primarily, Daniel was the primary leader and the main driver of this work to try to build to build Swan, the static analysis Swan for Swift, on top of SPDS instead of Voila, to make use of the new machinery that we have in SPDS with highly scalable and precise data flow analyses. So you can actually check out our Swan analysis framework now on the Maple Lab/Swan on GitHub, and there is tons of new features that we introduced this year. So now we can actually integrate with Xcode Build and SwiftC, the main two ways to compile Swift code on macOS and Linux machines. And we also introduced Swirl as the intermediate representation that we use in Swan, that has currently about almost full coverage for the Swift intermediate language that Swift compiles to, and has lots of really nice features like caching for caching, multi-threaded processing, selective parsing. All of these are features that enable faster processing of input files and reduce the repetition or the redundant work that the analysis will do to process input files. We also have library models. We have models for standard libraries that come with Swift, so that it enables modeling for these library dependencies that our analysis won't have access to, because they are either proprietary or they just don't ship with the applications. And we also have cross-module support in Swift programs and iOS applications. We also have various UI-enabled or testing-related features. Like we have annotation checkers, for example, if you want to do regression testing, especially when it comes to sources and sinks in a taint analysis. So you can easily use those annotations to quickly change your test cases and rerun your test cases to get immediate feedback about your code. And we have various code viewers as well. And most recently, the most recent addition to the framework was having call graph construction, taint analysis, and type state analysis. All of them are configurable for Swan. So now you can actually use Swan to do all these analyses using SPDS as the analysis engine for Swan, where it translates all those input code, all these programs, into pushdown system rules that can be processed eventually by the SPDS engine. And very, very recently this year in 2021, together with my PhD student Abdulali Bangash and my colleague also Abram Hindel, we were able to use Swan to detect energy bottlenecks in iOS applications, and specifically those bottlenecks that are related to the core location framework, and give suggestions to developers about how they can change their code to improve the energy efficiency of their applications when it comes to using the location services that iOS provides. So now that we have seen a little bit about the features that Swan has, and some of the recent advances that both Ali and Daniel have done with respect to energy consumption of the iOS core location framework, let me actually quickly walk you through a quick demo of Swan and its current capabilities. So right there we see a piece of code in Swift where we're running an application that uses the UI, and it's using the location manager to get the current location of the user of the mobile device, and it uses one type of location, which is fitness, which is one of the recommended ones. And here we can see the command line interface of Swan using Swan Xcode building the application using our core analysis engine. And here Swan also prints out the exact Xcode command that it uses to compile the application so that the developer knows what is exactly going on. It finishes in about 7 seconds to process everything, including all the dependencies. And here is a quick printout of the Swift intermediate language that Swan processed in order to generate its intermediate representation. And then we're running our Swan driver, which runs the analysis. Currently, most things work on the command line, but we're working also on some other user interface. And here we can see that Swan detected actually an error in the energy consumption of the application. And if we open the JSON file that contains more information about the analysis results, you'll see that Swan tells the developer that fitness is not optimal way to use the location service API and provides suggestions to use airborne instead, which is a better way to get the same kind of location information, but with less energy consumptions based on the studies that we have done. And here, if we just go ahead and recompile the application after that code change, it won't take as much time as before because we're not doing it from scratch and we are only doing selective processing. And now we're running Swan again, prints out some information, and now you can see that it doesn't detect any errors anymore. So we still print out the description of the usage of the visits location service and what advice it goes along with it, but the errors, there are no errors anymore. So you can see here that now with SPDS being the core analysis engine of Swan, we're able to detect energy bottlenecks in iOS applications and provide advice for developers to improve the energy consumption of their iOS applications on iOS devices. Also, very recently, things seem to have come to a full circle actually with the work that I did initially regarding partial program analysis and also SPDS when one of my master students, David Seacat, started working on BlueJ, which is a system that David came up with to enable precise SPDS summaries for Java libraries. So using SPDS as a highly scalable and precise data flow analysis to generate stubs for libraries that are more precise than the existing stubs out there, and even more precise than the Averroes library summaries that my PhD work used to generate 10 years ago or so. And I'm really looking forward to see how this project will end up and the eventual results that we're going to get out of this work, because there are some exciting updates that I'm looking forward to that we're going to get over the next few months. So this is some of the work that I've done regarding both scalability and precision with the work that I did with SPDS, with CogniCrypt, with Swan, with the energy efficiency for iOS applications, and also BlueJ, the work that David has been working on. So, how are things now? Are they still bad as I have seen them or experienced them 10 years ago when I started working on static analysis? I don't think so. I think things are much better now than before. You can see that in various different adoption of static analysis tools in industry. So here, Google, for example, is using static analysis techniques and tools for enhancing and hardening Android applications and enabling vulnerability detection for Android applications that would help developers improve the security of their applications. You can also see that at Facebook with various different tools that are deployed in practice at Facebook that scale to the large code base of Facebook. So tools like Infers, OnColon, and SapFix that enable detecting security vulnerabilities, and even automatic fixes and automated program repair tools that run at that large scale. And also you can see that at CodeQL, for example, which was part of SEML and now which is now part of GitHub, that enables continuous security analyses for open source repositories and also, of course, for your other repositories there. And now it is part of the GitHub Security Lab that enables a wide range of analyses that detect security vulnerabilities in your code and help you also correlate that with other vulnerabilities out there in your application. And very, very recently, as in last month at WWDC 2021, I have seen Apple also introduce a lot more features for their static analyzer for Xcode 13. So now you can actually do things like detecting infinite loops, detecting unused code, misuses of some APIs, detect null pointer exceptions, and this seems to work for Swift, C, C++, and Objective-C, and they have really fantastic visualizations that are tightly integrated and tightly coupled with Xcode as the main IDE that developers typically use to develop macOS and iOS applications. So I think that the future for static analysis is actually really vibrant with all this work that's going on and even more, like deep code, for example, using learning on large code bases to enable highly precise and highly scalable static analyses, and now they are part of SNCC. Code Sonar. Also, if you look at the SIG plan blog posts, you'll see a lot of work there introduced about how we can enable analyses for quantum programming languages. What about AI, and can we consider AI as a PL problem, and how static analysis can help with that, and so on and so forth. So I think there are various interesting challenges ahead of us in the static analysis community that we're just starting to scratch the surface of, and I'm really looking forward to seeing how the community would address these challenges in the future. So, like I said, we are almost there, but we're not there yet. So some of the challenges that I personally see that face static analysis tools specifically are going to primarily be related to usability, which is the third aspect that I've also been working on for the past few years, but I didn't get a chance to talk to you about today, but I'll be happy to talk to you about it as well later during the conference or later in general as well. So usability of static analysis tools is all about how we can integrate developer feedback, how we can make the developer easily signal, for example, that this is a false negative or a false positive that the analysis should take into consideration without having to, again, disrupt their workflow, disrupt the normal workflow. How the analysis can be even more responsive than what we have nowadays. And maybe we need to leverage hardware acceleration, perhaps, or recent advances in computer architecture that can enable even faster analyses that doesn't necessarily overload or overwhelm the main pieces of hardware that developers use on their machines for developing or for development. How can all that enable even further seamless integration of static analysis tools into the development environment of developers without disrupting their workflow? And finally, how we can build tools that can be customized and provide tailored experiences to the developers themselves. That can go all the way from just having simple configurations to the tools, to learning from how the developer interacts with the tool, how the developer uses the tool, when do they use the tool, and having that data and crunching all that data and enable and using it in the static analysis tool itself to provide the experience that would convince the developers to look at static analysis tools the way they look at compilers or the way they look at IDEs nowadays. So that they can use it as often and to the full extent and to the full potential that I think a static analysis tool can provide to developers. So at the end of my talk today, I would just briefly like to summarize what I've been discussing today. So first, I talked about static analysis and how it can enable not just detecting, but also potentially fixing many of the security vulnerabilities or many of the software bugs that we have seen in practice that range from simple programming errors to race conditions to life-threatening bugs in medical implants. Some of the work that I've been doing with my collaborators over the years regarding scalability and partial program analysis that was done earlier in my PhD, and later the work that I've been doing with my students in the Maple Lab and my collaborators regarding building a scalable and precise static analysis framework for Swift called SWAN, and how we used SPDS or synchronized pushdown systems as the internal and the core of the static analysis engine of SWAN, and that enables all these features that we have for Swift that we couldn't have before we implemented SWAN and presented it a couple of years ago. And at the end, I shared some of my thoughts about the future of static analysis and the challenges that I see ahead of us over the next few years, and how I'm very hopeful and I'm very excited to see how the whole community would go about tackling these challenges over the next decade or so. With that, I'm very grateful again to the A2 and to the selection committee and all my mentors and all my colleagues and all my students for whom they are the main reason I'm here today talking to you, and I'm very grateful for that. And I'd like to thank you all, and hopefully I'll get to see you around at the conference, maybe virtually this year, hopefully in person over next year, maybe the year after. Thank you again. and I hope you enjoy the rest of your time at the conference.